Almost certainly our entropy question will centre around Gibbs free energy and the Gibbs free energy change. Now the Gibbs free energy change combines the three things which determine whether a reaction will be feasible or not, and that's temperature, entropy change and the enthalpy change. Perhaps at this point we'll just note that entropy change, we're in joules, whereas the enthalpy change is in kilojoules, and we'll need to watch out for that when we do the equation. So here is the equation for the Gibbs free energy change, and that's delta G is equal to delta H minus T delta S, so T multiplied by delta S, and this is an equation that we need to learn. So what does it tell us? Well, we put the numbers in, and the equation will give us a number, and that number will be either positive or negative depending on the values that we've put in, and if the value is less than or equal to 0, that means the reaction will be feasible. Let's look at the example in the notes and we'll work out delta G for a given reaction. The reaction is between sodium hydrogen carbonate with hydrochloric acid. Let's pop the equation down. There we go. So sodium hydrogen carbonate, hydrochloric acid gives us sodium chloride, water and carbon dioxide. See if you can remember how to work out delta H for this reaction. So the sum of the enthalpy of formation of the products, take away the sum of the enthalpy of formation of the reactants. So those are the numbers that we'll put in. So they're given in the table there. Have a go at putting that in your calculator. And we should have got 31, and that's kilojoules per mole. Now do the same for delta S. Remember, that's the sum of the entropy of the products, take away the sum of the entropy of the reactants. And we should have got plus 196.4, and that's joules per Kelvin per mole. And so to combine all the data that we've got, to work out delta G, we've got delta H, so that's just 31, and we're subtracting the temperature times by delta S, and going back to the top of the page we can see the temperature is 298 Kelvin, and the temperature needs to be in Kelvin, so that's all good, and we're multiplying that by delta S, which was 196.4, but remember that was in joules, whereas the enthalpy is in kilojoules, so divide your entropy value by 1000 and see what you get. And I worked that out to be minus 27.5, and that will be in kilojoules per mole. But really the bit that I'm most interested in is that that is negative, it's below 0, and that means that at this temperature this reaction will take place, it's feasible. To summarise, for this particular reaction, So it's an endothermic reaction, so why can it take place spontaneously? Well, yeah, delta H is positive, but because delta S is also positive, the balance means that delta G is negative.